So right at the end of class on Monday evening, we were talking about this last type of reaction, which is an oxidation reduction reaction. These are reactions that occur in pairs, and it's based on the movement of electrons. And I use oil rig as my memory device to remember that when something is oxidized, electrons are lost. Remember, when electrons are lost, the item becomes more positive, and reduction is gain. And so as electrons are gained, the item becomes more negative. And to be able to figure these oxidation reduction reactions out, you first have to remember the charges or oxidation numbers that we've been talking about for the various groups, and be able to use those to figure out the items that you don't know. So let's look at some examples. Well, first, each element is always 0. Even if it's a diatomic element, it's still 0. And so let's take a look at these other examples. So what's the charge of H here? Well, I know that oxygen is always 2 minus because that's what the previous slide said, and that's true. So that means that each of these hydrogens must have a 1 plus because I see we have 2 of them. So positive 1 is the charge of hydrogen. Because hydrogen, remember, only has that 1 valence electron. Sometimes it can be a -1, that it's going to gain an electron to fill its outer shell and satisfy that octet rule. All right, so let's take a look at each of these chemical species. And so one of the things I've got to figure out is that we've got 3 oxygens. I know that oxygen is a -2, so that means that's a -6. All right, and so hydrogen, in this case, must be a +1, which is what it often is when it's bonded to a non-metal. It's either going to be a +1 or a -1. So that means that this nitrogen must be a +5, which I hadn't necessarily expected, because that's going to allow the compound to equal 0. So let's take a look at this last one. So we've got O. We know that O is -2, and there's 4 of them there. So the total is going to be -8. K, of course, is a group 1 metal. So it's going to be +1. So that means that Mn here must be +7. Because obviously then it's going to allow that formula to equal 0. And so again, I'm just kind of playing with them and figuring them out, trying different things to see what works out. And then what you can do is you can use these in an oxidation reduction reaction. So here's an example of an oxidation reduction reaction. Yes, it's also a single replacement reaction because zinc is replacing iron. But then zinc is also with NO3 as a product. All right, and so let's take a look at this reaction. So it's a kind of an unusual reaction. All right, in this case, I'm going to keep the NO3 together. I'm not going to keep them out separate. And I know that it is a -1. Zinc, because it's an element, is all by itself, is going to have a 0 charge. And so this means that Fe must be +3. The other way I could have done that is I could have looked at, there we go, this 3 here. Obviously, it had to have come from iron, so it's got to be a 3+. So that would have been another way that I could have taken a look at that. So now let me look at my products. NO3, of course, nitrate is a -1 charge. Fe then had to be a 2+. And so if I look at Fe from reactant to product, I can see that my charge has been reduced. So obviously, And if I look at my zinc, I see, oh, wait a second, zinc went from, and I didn't have that in there, went to a 2 plus, obviously. And so zinc has been oxidized. So that means that iron has been reduced. So that's how we do those types of equations. Okay, there we go. We've got it now. So we see these oxidation reduction reactions in real life all over the place, in batteries, in electroplating things, in photosynthesis and rusting.